Okay, good morning, everyone. Thank you for being here. And thanks to Divra for inviting me and giving me this chance to speak to you. So today I want to talk about the existence of physically consistent quantum master equations. And this is a recent joint work with Manas, Abhishek, and Achal. Okay. So I want to start by giving you a brief background of open quantum systems and quantum master equations. And then we'll talk about the three main results. So basically, we show that the right field equation, which is widely used, will almost always violate complete positivity. It's known that the right field violates complete positivity, but we have a system independent proof that is interesting. And then we'll talk about Lindblad QMEs that obey properties that we would typically like them to obey, which is they should preserve local conservation laws and they should thermalize. And then I'll end by giving a brief summary. So let's start with the background. So a very brief introduction. In open quantum systems, we typically have quantum system that is connected to a bath, and the system-bath interaction is typically weak. For some parts of today's presentation, we'll assume weak coupling. For some other part, we won't. And we use epsilon as a dimensionless parameter that controls the strength of the coupling. And so you want to figure out what the system is doing at a later time t, but you don't want to evolve the full system plus bath setup and then trace out the bath to see what the system is doing at any time t, because the bath is too big and this is typically infeasible. So a quantum master equation is just an equation of motion for the density matrix of the system. And we want to derive one that is good in that it is correct and predicts realistic things. So for the entire duration of this talk, we are interested in Markovian QMEs, which means that the equation, the rate of change of rho at any time t, where rho is a density matrix of the system, is going to be a linear function of the state at that time. It does not depend on the history of the time evolution. And typically, we will also be interested in or look at quantum master equations derived under the Born approximation, where you argue that because system bath coupling is small, we can sort of write an equation to second order in epsilon. You might ask where is the first order term in epsilon, and typically you can choose your setup such that the first order term disappears and you're only left with the second order term. Right. So the overarching sort of series of questions you can have in so far is, well, how well do such equations derive the original setup? How can we derive them? What properties should they have to be physically meaningful? So on and so forth. So I want to start off with the requirements that we want to impose on the quantum master equations. Yeah.
So why was it that you said the first order term?
Basically, you can always choose the sort of, it's not that it always disappears. You can always study an equivalent system where the first order term disappears by adjusting the Bath Hamiltonian, I think. So in practice, because we want it to disappear and it doesn't really change the physics, we'll always consider situations where we've done this and the first order term is not there. Okay.
Like kind of an interaction picture.
No, I don't think it's just you want certain. Yeah, no, I don't think it's the interaction picture thing.
Kind of symmetry that can help us understand.
I think maybe after the talk I can give you I can show you an equation that does this, but right now I don't know how to really explain. Sorry. Okay. But I mean, for now you can just consider that it disappeared for some reason, and then later on I'll motivate why you can make it disappear. Okay, so what requirements do we want on QME? So we want a quantum master equation to preserve all properties of the density matrix. So it should always output density matrix that's completely positive, and it should preserve trace and so on and so forth. So this is nice because it's solved by the GKSL theorem. We don't really need to worry about it. So we would also like the QME to preserve conservation laws for local observables. So I'll make this a little bit more precise later. But essentially what I mean is that if you connect a system to a bath, and let's say you look at the steady state values of things like spin current or energy current along the chain, then you should get continuity in the sense that the current going from the second to the third should be the same as the current going from the third to the fourth, if the third spin is not connected to anything. So things like these are local conservations of stuff like charge, energy, and spin, and you would want them to be satisfied. And you would also like your quantum master equation to predict thermalization. So basically, if you couple it to baths at the same temperature, inverse temperature beta, then the steady state that you achieve in the limit of strong small coupling should be the Gibbs state of the system, right? And here the limit epsilon tending to 0 is important because if epsilon is finite, which means the system bath coupling is not exactly 0, then you will expect some contribution from the bath. So it's only the 0th order contribution of the steady state that has to be the Gibbs state, right? And so we had previously looked at these three conditions and analyzed them separately. But in some sense, you can view what we're doing right now as combining all three. So earlier we had ways to check whether 1, 2, and 3 were satisfied for any given quantum master equation, but not if all three were satisfied together. There was no way other than checking them independently. And now we want to really combine them and say, I want something that does all three. What can I say about such equations? Okay, so just for completeness, I want to give you a brief, just mention the GKSL theorem. So basically, what this says is that if you want to preserve complete positivity and trace of the density matrix, and you're describing Markovian dynamics, then your equation has to be of this form. And I guess I can point here. So this HLS term is, we refer to it as a lamp shift Hamiltonian. It's just some Hermitian Hamiltonian that you get from the bath. And the only constraint on the next part, which I'll call the dissipator, is that this gamma, which is a matrix, it has to be positive semi-definite. And the FIs are orthonormal bases, which are chosen with the constraint that the last one has to be equal to normalized identity. So this is the generic form of a Markovian quantum master equation. So I'll refer to this as a Lindblad form. And if you want to check whether your particular quantum master equation satisfies, say, whether it preserves complete positivity or not, all you have to do is massage it to get you this form and then check whether your gamma matrix is positive or not. And if it is, then you're fine. You're in Lindblad form. Okay. And yeah, you might be familiar with the other variant where you can diagonalize gamma and essentially get an equation where you don't have cross terms in the second part. Right?
What is HLS?
Sorry?
What's HS is the system?
Yeah, so HS is the Hamiltonian of the system.
RS is the coupling.
So HS is the Hamiltonian of the system. HLS is the lamp shift Hamiltonian. It's not coupling. It's just something. You can think of it as the additional Hamiltonian given by the bath, right? Okay. So we are going to be interested, or we're going to study a specific kind of a setup. So we're interested in setups where your system can be partitioned into two parts. One part is the stuff that couples to the bath, and the other part is the part of the system that has no coupling to any bath. So we need this for reasons that will become clear later. And I'll call the part that couples to the bath HL and the part that doesn't couple to the bath HM. Okay, so I'll call the Hilbert space script HL because HL is not the Hamiltonian, it's the Hilbert space. So there's like abusive notation there. So I don't care about the kind of coupling between the system and the bath. I also don't care how many baths are attached. I just need there to be a part of the system that doesn't couple to any bath. And we're good to go. And our choice of basis will come in important later on. So we want to choose a particular basis to work with such setups. And what I'm going to do is I'm going to pick orthonormal basis Fi that only exists on the L part of the system. which has the last element as normalized identity on IL. And the second basis to be orthonormal on the remaining part of the system that doesn't couple to any bath. And again, the last element of that basis is going to be normalized identity. And then I can construct the full basis by just doing a tensor product, right? And yeah.
What is our
So L is just, if you look at the diagram there, L is the part of the system that couples to the bath, and M is the part that doesn't. That's it. Right, so we're going to get the complete basis for the entire system by doing tensor product, and this basis satisfies the requirements by the GKSL theorem, as in it's orthonormal, and the last element is normalized identity. DL and DM are the dimension of HL and HM respectively. And what I'm going to do is I'm going to change the indexing of my basis so that the first few elements of Fi here are going to be a basis element on the L space and tensor with identity on M, right? And I can always do this, and this will make certain things cleaner. So I'm just simply changing the way I order these basis elements, and I'm allowed to do that. Okay. All right. So let's talk about the first result, which is a violation of complete positivity by Redfield. So, I'm gonna go through the derivation of Redfield very briefly, and just sort of mention the steps needed to get that. So you can write down a generic Redfield equation like this, where you see that it's you've done Born and Markov, so it's epsilon. The epsilon square part is the effect of the bath, and you have this evolution according to the system Hamiltonian that you always do. And we're gonna assume a very generic system bath coupling, which is of this form. We make no other claims on this type of system bath coupling, apart from the fact that we know it couples to only the L part of the system. Okay, and if you just plug this system bath coupling in and you see what you get, then you get an equation that looks like this. So the SL1 and SL2 are some operators that will show up. We don't care about them. The interesting thing is that you have SL dagger here as is, without any, you just have SL and SL dagger here, and that's going to be critical. So now what we can do, there's some operators that show up. They involve integrals over baths, and there's some operators on the system. Yeah, they're not the same. So it's not a power, it's just there's some operator, I don't care about them, right? And the reason why I don't care about them is I'm going to now expand every operator that showed up in Redfield in this basis that I've chosen. And SL1 and SL2 and the daggers I can expand in whatever way I want. The critical ingredient is that because I know that my system bath coupling only couples to L and not the M part of my system, I know that certain elements in SL expansion and the expansion of SL dagger will be 0. Because I know that SL lives only on the L part of the system and not on the M part. Which means that, and because I chose all the basis elements that live on that identity on M to be the ones that are numbered from 1 to DL square minus 1, I have that these coefficients in SL and SL dagger expansions have to be 0. So F is the basis that we chose a few slides ago. So F is just an orthonormal basis of. Yes, F is an operator. Yeah. Also, yeah, and it's orthonormal in the sense that trace of Fi dagger Fj is delta Ij. So F is an operator on the system, and currently I'm not claiming that it is physical. I just require F to be an orthonormal basis of operators, and that's it. I'm not connecting it to any physical picture, right? Okay, so we have these certain elements that are going to be 0. So now we can plug this into our Redfield and try to massage it and get a thing that looks like a Lindblad form out of it, and you do get something that looks like a Lindblad form, where the matrix that sits inside the dissipator term is given by okay, I seem to have lost my mouse. Yeah. Yeah, okay. So that's given by this expression gamma alpha alpha tilde, sorry. Okay, so now we know that the positivity of whether right field preserves complete positivity is going to be determined by whether this matrix is positive or not. Okay, so now since some of these coefficients are 0, I can see that the structure of gamma is of this form. Just look at gamma alpha tilde and put both the alpha and alpha tilde to be greater than dl square, and you'll see that each of the 4 terms is actually going to be 0. And so any situation where both the indices of gamma are greater than dl square is going to be 0. So now I'm interested in the positivity of a matrix that looks like this, right? And now we claim that, okay, if gamma is a positive matrix, then any 2 cross 2 subblock has to be positive. So I can pick an index I that is less than dl square, an index j that is greater than equal to dl square, and I can construct a 2 cross 2 matrix obtained by intersecting sort of those 2 rows and those 2 columns. And I see that if I do that, I need every gamma prime that I can construct in this intersection of rows and columns way to be positive semi-definite. And I mean, a very simple calculation will show you that this is only going to happen if the off-diagonal elements are actually 0. So we already know that gamma is going to be Hermitian based on the way we derived it. So we basically just need one of them to be 0 for the other one to also be 0. And I mean, the way you see this is just write down the characteristic equation for the eigenvalues of this 2 cross 2 subblock, and then you just look at it and convince yourself that the off-diagonal blocks have to be a 0. Yeah.
The definition of the just have the eigenvalues of the matrix.
Yeah. So just to clarify, we mean positive semi-definite. So every eigenvalue has to be greater than equal to 0. We are okay with 0 eigenvalues. Okay, so all right, so because I can do this for every I less than dl square and every j, the requirement on gamma to actually be positive semi-definite is that the entire off-diagonal block has to be 0. And this is not going to be true in general. So the conclusion is that right field will violate complete positivity. Yeah. Okay. Yeah, so one way you can think of this is that gamma being positive is the same as, I can write, right? Just in brief. Yeah. So I need something like this to be greater than, okay. I need this to be greater than equal to 0 for all vectors v. Which means that, and because I can pick my I and j.
I guess you can just pick the places.
Correct. You put zeros in every other place and you just pick those 2, and then you would require that block to be positive as well. That's it. Yeah.
So my understanding is that this gamma matrix is essentially the rates of decay of populations and the populations. So
yeah.
What is the physical implication of this matrix gamma to be not positive?
So the physical implication is given by the GKSL theorem. So I said that you want an equation that always gives you a matrix, always gives you a density matrix that is positive and has trace 1. So if you have a gamma that is not positive semi-definite, and then you try to solve for the expression of rho at time t, you might get a density matrix that is not a positive matrix. So you'll have negative eigenvalues, which is inconsistent.
Thank you.
Yeah. Okay. So all right, so we were here, we said that the off-diagonal blocks have to be 0, and this is not true in general, so RE violates complete positivity. Again, this was known before, but it was, to the best of our knowledge, it was known in specific cases. What we are saying is generically, if you have a part of the system that you don't couple to and you try to write down RE, you will mess up. Of course, there's a caveat. You could say to me that, well, you didn't really show that the off diagonal blocks can't be zero. So maybe they're zero in some cases and they cancel and you just don't know about it. True, but if the off diagonal blocks happen to magically cancel out and give zero, then the RE dissipator will be local. And by what I mean by that is you'll only have the first block in gamma showing up. And because you chose your bases to be in this form, you chose the first few of them to be identity on M, the RE dissipator is essentially not acting on the M part of the system at all. So then I would say that, yeah, RE will violate complete positivity in these situations unless the RE dissipator happens to be local. Yeah.
Is this local here related to local concentration?
Yes. Yes. So I guess that will be clear in a few slides. Okay. Yeah.
So why did you set wasn't right R matrix 0?
Oh, because if you just look at, so we said that if you plug in this basis, then you get a matrix like this. Now just look at gamma alpha and you put both alpha and alpha tilde greater than DL square. We know that they're going to be zero. So this term goes to zero, that term goes to zero, every term goes to zero. Right? Okay. Okay, cool. So I'm done with my first claim, which is that
using this, now that you know what's the condition for not getting positivity, it's hard to go back and look at the Hamiltonian and design plans such that you will actually see.
yeah, so
Can you go back and listen to procedure now that you know what gamma will
correct.
do?
So in some sense we can. Okay. So I think maybe we haven't done that. So we haven't gone back and said, well, how can we fix RE this way? So we sort of took it in a slightly different direction where we say, okay, obviously you want to fix RE to avoid this, but you don't want to break anything else that Redfield does well. So that brings us to sort of the next question. So I don't know if I'm answering your question, but yeah. So okay, so we know RE has this issue and it's almost always generically going to be the case. So what can we do? Well, what can we say about Lindblad quantum master equations that preserve local conservation laws? Right? And what I mean by local conservation laws is the following statement. So I'm interested in looking at the rate of change of an observable that only lives on the M part of the system, that is not coupled to any bath. Right? And IL is identity on L. So if I try to evaluate the left-hand side of this equation, I'll get the right-hand side for the original setup without any approximation by just doing sort of Heisenberg equation of motion and for the RE. So Redfield satisfies this equation. Okay. And therefore we don't want to break it. We want our Lindblad quantum master equation to also reflect the statement. And in some sense, what this is saying is that because OM lives only on the part that's not connected to the bath, when you try to compute this, it doesn't in some sense see the bath directly. It sees the bath in the way rho at time t is different, but it does not, you don't directly see any bath dependence or in this equation at least. And basically, when you have something like this, what you can write down is that the right-hand side is the net current of this observable OM from L to M. So basically, you can put, let's say you have a spin chain, you can put your OM to be the net magnetization of that part of the chain. And then you can write down this expression and you can identify this as the spin current going from L to M. Right? And then obviously that has a nice interpretation in terms of the rate of change of total spin in the M part. And all of this works because the M part is not connected to any bath, basically. So for example, in the steady state, you would expect the left-hand side of the first equation here to be zero. So you should also get the right hand side to be 0 because that's what you identified as the current. And yeah, if you violate this, then you lead to violation of local conservation of things such as spin and charge. Yeah.
I don't understand the meaning of local here. Like, so when you say local, is it local to the end system?
Yeah.
And so it's not nothing to do with the alpha.
So I guess there are two ways in which I'll mean local then. Yes, in this particular, like in this slide, when I say local, I mean that the thing that I'm identifying as the current from L to M, that thing should obey conservation laws in the sense that if I'm in the steady state, so if I've evolved for long enough and my state is not changing, then I know that this guy is 0, correct? Because my rho is not changing, so obviously no observable, no expectation value can change. But then the right hand side should also give me 0. So if I compute the steady state according to my master equation and I evaluate the right hand side, it should always be 0 for every steady state, because there is no spin, charge, current, whatever you want going into that part of the system. So in that sense, I mean local conservation. Right.
What would be the like opposite of local?
I mean, I think opposite is sort of a
Global?
yeah. So I mean, I just mean local in the sense that this quantity is not. I mean, it's not exactly. Yeah, I don't think I have a good answer to your question. What would be the opposite of local? But yeah, I mean, in some sense, by local, if I can give you an example, I mean that I have a spin chain, and I connect the first and the last spin to the bath. That's fine. But then the current of energy current going from 1 to 2 has to be the same as the energy current going from 2 to 3 in the steady state, right? I would expect this because there's no buildup of energy at the second spin because it's in the steady state, and I want that to be satisfied. So in this sense, I mean local conservation.
So it's conservation that is true at every single point.
Yeah. So we have decided to look at this particular point where you have a L and M system, but yeah, you would want it to be true at every particular point. Yeah.
So you were just looking at one particular point.
So if you demand local conservation of things in the part that's connected to the system, connected to the bath, then it's a bit difficult because people can always say, well, sure, the currents don't exactly match up, but that's because something is going to the bath because the bath is connected to that part, right? So you can only easily talk about this if you don't have the bath connected. So we are okay with any local conservation in situations where you are looking at an observable on the part where the bath is not connected. Okay, sorry, there was a question. Yeah.
Actually, I'm a bit confused. Spatially local or temporal? From the dissipator, it should be when I'm inserting P instead of P,
Yeah.
it should be temporally. But it seems from change that in a spatial.
So right now it is basically spatial. So we have said like the model I have in my mind is there's a bunch of spins connected and you connect the bath to the first 2 spins, but not to the next 2.
Okay, so,
So-
temporally it's local again.
Uh,
If you will insert in your dissipator T instead of T prime, when
Yeah.
you are moving back to schedule the picture, so that is temporally local. So now I understand you are, I mean, it is spatially local.
yes.
So both temporally as well as. Is it correct?
So this equations are time local.
So time local, if you will see the dissipator.
Yeah, it's done.
Now, that is time local and it is now spatially local.
Well, conservation locally. Okay.
Yeah, I mean, I think I can't. Sorry. Right. Okay. Okay. So I'll move on to the statement we can make about such setups, and we're claiming that any quantum master equation in that form which you require, which satisfies local conservation laws, it must have Lindblad operators and lamp shift Hamiltonians that are identity on the part of the system not connected to the bath. So they have to have this form. You can't let them act on the M part of the system non-trivially. So at this point, you might say, well, didn't we know this already? You started off by saying that the system couples to only L. So obviously, the Lindblad operators and the Lamb-Shift Hamiltonians is also going to act only on L. Well, the answer to that is, well, no, because many approximations that people routinely make to derive Lindblad equations don't obey this. So you can have a system that's only connected to the first two sites, but when you write down and try to derive a Lindblad form of a quantum master equation out of that, you will get that the Lindblad operators act on everything. So this is not always true for QMEs that are being studied these days. The second claim is, well, isn't it obvious that this has to be the case? If you think that, then I'll just say that Redfield does not obey this. So Redfield does not act only on the part of the system connected to the bath. It acts on the entire system, but it somehow manages to conserve local conservation laws. So there is you really need the fact that you're conserving local conservation laws and you have a Lindblad form to really make this claim, because Redfield acts on the full thing and is completely fine with respect to conservation laws. Okay. So I just want to give you a very brief sketch of the proof because it's a lot of algebra. I don't want to go into it. So essentially, we want to start out by writing the most general form of Lindblad quantum master equation, where we demand that obviously this H tilde is the Hermitian matrix, Hermitian operator, and gamma tilde is a positive semi-definite matrix. And we demand conservation laws to be satisfied. So we write down the rate of change of the observable for this equation and demand that the right-hand side should be exactly what we want it to be. Then you want to use the fact that because you chose a particular basis, which is identity on the M part for the first few elements, they commute for certain i's, and so you use that commutation relation. Then you want to use the fact that the way you constructed this basis was a tensor product of bases on L and M separately, and each of these bases are orthonormal. So when you use the fact and then you trace out L, you can really use the orthonormality of the basis on L to get rid of certain terms. Finally, you'll get a big giant thing. You want to convert it. Basically, you want to use the matrix to vector mapping, and you at some point just do this conversion to a vector for your density matrix. You trace everything, and you end up with a condition that looks like that. So all this is saying is that the sum of certain elements in my dissipator matrix have to be 0. If you recall, we already sort of get that from Redfield, right? If you look at the Redfield dissipator, if you remember that we had a 0 block on the second diagonal block, that's essentially satisfying this relation. Okay. So, all right, this seems very, you just get like sum of certain elements is 0. What can we do with it? Turns out you can do a lot. So we have claimed that, okay, to satisfy conservation laws, I need
Conservation or local conservation?
local conservation. Yeah, so I'm going to use the term interchangeably, probably. So sometimes I won't say local, but what I mean is exactly the first equation I put out at the start of this section.
In your previous proof, where does the locality come in?
The locality comes in because I'm demanding that, I'm demanding that this equation has to be true for all observables OM that only live on M. I'm not writing it for the, you have to have identity on L. So you can only have an observable on the M part.
So you're assuming locality to be true first, and then you're proving something else.
Yeah, so I'm demanding that if I have a QME that obeys this, what can I say about the quantum master equation? That's the exact question. And so the way I'm doing this is I'm saying I have a QME. I demand that it obeys my local conservation law. What can I say? And I say that if it obeys local conservation laws, then this condition has to be true. And this condition lets you do a lot because you can combine it with positivity. So you can say that, look, I need these certain elements to be 0, they're on the diagonal, and I require positivity. So because you require positivity, you can't let any of these elements be negative because you want a positive matrix. So all of them have to be identically 0. Because if you put one of them negative, then you'll mess up positivity, and the sum has to be 0. So there's only one way. And then we go back to our standard tool now, that if you want gamma to be positive, any 2 cross 2 sublog has to be positive. You construct every 2 cross 2 sublog you see for gamma tilde, and then you again claim that, well, the only way this is true is the off diagonal is 0. So essentially, in a positive matrix, if you see a 0 along the diagonal, that entire row and that entire column has to be 0. Otherwise, you are not going to get a positive matrix. That's sort of what this is saying. So, okay, if you now use that in the structure we have, then you get a bunch of zeros along the way. And again, because you only have the first block to be non-zero, our basis, recall that our basis was Fi tensor Im in that region. So you have a local dissipator. And I'm not going to show you how you get a local lamp shift as well, but it's just a little bit of algebra to plug in this kind of a dissipator and then ask, what do I need the lamp shift to be? So, okay, what are some implications of this statement? So we have that complete positivity plus local conservation laws will require local QMEs. So that means that non-local QMEs that are in Lindblad form will necessarily violate conservation laws. So we have, for example, this all started because at some point we noticed that ULE, which had been derived to have very good accuracy with respect to right field, was violating local conservation laws. That was kind of what started all of this. You'll also notice that we sort of get our first right field result in some sense for free, because now we can say that, look, I know that RE preserves local conservation laws, I can show it. So if RE preserves local conservation laws and is manifestly non-local, then it will definitely violate complete positivity. Otherwise, it would be a violation of this theorem I just proved. Okay, another nice thing about this is that you can analyze other QMEs reasonably easily. You just have to look and see, is it in Lindblad form? Okay, if it is it local? That's it. And usually it's fairly straightforward to tell whether a QME is acting locally or not. And the final claim is that this is true for all Markovian QMEs. We didn't make any assumptions on coupling strengths. So this is just true in general, without demanding weak or strong coupling. Okay, and typically I would say that even if you do weak coupling, we see that the violation of this conservation laws is scales in the same way as the current itself, if you check scaling with respect to epsilon. So typically the current will be of order epsilon square, but the difference between two currents on two sides will also be of the order epsilon square. So yeah, that's it for this part. So okay, we seem to have a handle on Lindblad QMEs preserving local conservation laws. We just write it in Lindblad form and it should be local and we're done. Can we also add in the requirement for thermalization? And this is a little bit harder, but it turns out you can. So we had shown a necessary condition for thermalization, which is that you can. So you write down your QME like this, and then you look at the sort of the effect of the bath. So you look at L2, and then you demand that the diagonal values of L2 acting on rho thermal for the energy eigenbasis of the system has to be 0. So here EI is the energy eigenbasis of the system, and rho thermal is the Gibbs state. So you need this to be 0 for rho thermal to be the 0th order contribution to the steady state. Okay. All right. So what we do is we define tau, which is just the sum of absolute values of these diagonal elements that should be 0. And we claim that we get thermalization only if tau is 0. Because only if tau is 0 can I. So all of these equal to 0 is exactly the same as demanding tau is 0. It's if and only if. Okay. All right. So we now only need to look at tau, which is one quantity and nothing else. And we can write down a local Lindblad QME in this form, where I've explicitly made sure that it's local in that every basis element you see here is identity on M. So I'm going to get a local dissipator, and the lamp shift is also identity on M. And I take an explicit epsilon square dependence out. So all of this is dependent on weak coupling. So you do have small epsilon square that's sitting entirely outside of this. So we can, yeah.
The eigenstates there, right?
Yeah.
EIs?
Yeah.
Are those the eigenstates of the system or the?
System.
Right, so why is it that it needs for thermalization that the condition that the dissipator needs to act on the thermal state? So thermalization would be just that the diagonal entries of your thermal state are just the Gibbs occupations, right? What do you have there?
No, so I require that a steady state of my quantum master equation, the 0th order contribution of that steady state, if I look at scaling with respect to epsilon, is actually the Gibbs state. So if I can just go back. Okay. Yeah, so I require this. So what this is saying is that if you, the limit epsilon to 0 is saying that go to the steady state, look at the 0th order contribution of the steady state with respect to epsilon, and that has to be the Gibbs state. Right?
Right, so you're adding the, okay.
Right?
Yeah,
So,
yeah.
okay. And I mean, I think this is a pretty robust way of checking thermalization, because we're not demanding certain observables match what you expect from the thermal state. We are demanding that the state should be close to the Gibbs state. And we are making precise by what we mean by close. It is that the 0th order contribution should be exactly the Gibbs state. The epsilon square contribution can be whatever, we don't care. Okay, so right, so I can then write down local Lindblad QME. So just because I wrote this down, I don't have to worry about Lindblad form. I don't have to worry about local conservation loss based on a previous theorem. Now I just ask, can tau be 0 for such a QME? And so we can, that leads us to introduce this thermal optimization problem, which we can call TOP, which is minimize tau by varying the lamp shift Hamiltonian and gamma, subject to the constraint that gamma, sorry, HLS has to be Hermitian, gamma has to be positive, and trace gamma has to be equal to 1. So obviously the HLS Hermitian and positivity of gamma constraint makes sense. We want a valid Lindblad form. Why do I have the trace gamma equals 1? It's to avoid the trivial solution of basically lamp shift is 0, gamma is 0, because that would almost like trivially imply tau is 0 because L2 doesn't exist. So yeah, so we want to avoid a trivial solution. So I want to motivate why this trace gamma equals 1 is not, I'm not imposing any additional constraints on the problem, because ultimately I sort of care about whether tau is 0 or not. And my claim is that if you have a gamma and H, okay, that's a typo there, the gamma should not be LS, but if gamma and HLS lead to tau equal to 0, I can scale them up and tau would still be 0, because tau is a linear function of gamma and H. So I can scale them up any way I want, and whether or not tau is 0 doesn't change. Also because the way I constructed it before, I have an explicit epsilon square sort of scaling thing outside. So all I need is for you to give me a gamma, and then I can pick whatever epsilon I want to get whatever weak or strong coupling I wish to get. Okay, so let tau opt be the optimal value of this optimization problem. I will claim that if tau opt is less than some tolerance delta, which is given by numerics, then the desired quantum master equation is possible, because there is an assignment of values to gamma and the lamp shift Hamiltonian that gets me thermalization. Otherwise, the desired QME is impossible. Yeah.
So like earlier I was paying attention to like the thermal state only the tau is 0, but not here. So like you can tau is 0 without thermal state.
So right. So if tau equals 0, then I can claim that there is some steady state that is rho thermal plus epsilon square contribution. But there could be other steady states as well. So the problem is there could be multiple steady states. And if tau equals 0, then I can claim that one of them is the thermal state, but the other ones could also be non-thermal. So I cannot claim that if you start off a system and evolve for a long time, T, you will actually get to the thermal state. You might get the other one. So that's why I am not saying if and only if.
Why do you doubt that you can thermalize in the first place?
Oh, because I mean, you can write down QMEs that don't. You can write down a QME, compute its thermal state, and see if it's close to the Gibbs state of the system, and you will find that it's not at all close. So there are QMEs being used that don't thermalize. So yeah, I mean, not every QME will actually give you a steady state that's thermal. So yeah.
So should we think about achieving thermalization as an objective and
Yeah.
for proper Fatima conversion, since it's decoupling, should the setup is of the system embedded within that. For these types of systems, yeah. Maybe cases when you are not reaching thermalization. For these types of systems, you should thermalize. But the quantum question can be important, yeah.
Okay, so this is a conclusion. If tau opted less than delta, desired QM is possible because this minimization problem managed to get tau to be small. Otherwise, it's impossible. Now, all of this works if you can actually compute the optimal value of this problem reliably, precisely, exactly. So, well, it turns out we can, and that's because it can be cast as a semi-definite program. I mean, in principle, this seems very hard, right? How do you search over all possible positive gammas and all possible Hermitian operators H? I mean, the space is too big. How do you actually search over them? Even if you did some sort of gradient descent type calculations, you would never know whether you actually hit the actual optimal point. You might be close, but you don't know how close you are. So this fact that this can be cast as an STP is really, really important because STPs have some very nice properties. So semi-definite programs is a subfield of convex optimization. They can be solved efficiently. They can be solved using standard high-level programming languages like MATLAB or Python. And essentially what the theory lets you do is you use this notion of duality to get both an upper bound and a lower bound on the optimal value. So if you give me a semi-definite program as the one on the previous slide, I can construct a dual problem to that. And then if I solve both of them, then I get an upper bound and a lower bound on the optimal value. And the better I can optimize both these problems, the better upper and lower bounds I can get. Usually we can get the lower bounds and upper bounds to pretty much match exactly. And if that happens, then I've exactly hit the optimal value. And I know for sure that you cannot do better than this. So this is a really important characteristic of this formulation, that I am optimizing tau. Yes, I'm getting a value of tau opt from this SDP, but then I can claim that you cannot do better. There is no way to do better because this is an SDP and I know both the upper bound and lower bound on tau. Okay, so I think these are really cool and they're widely used in quantum information. If you're interested, I would recommend Jamie Sikura's QCrypt tutorial or this website. Yeah.
So if your system contains a continuous degree of freedom, like position or something,
yeah,
then these gamma matrices become.
So this is finite dimension.
Okay.
Yeah.
But I guess maybe suppose I have a degree of freedom in my system which is large finite dimension.
Yeah.
Then doesn't those gamma matrices also become large dimensional?
Yeah.
And so then solving this STP becomes hard.
Yes.
Scales with the size of the gamma.
Yes. Yes, definitely. So you can't just yeah, if it's like a 500 dimensional system, then it's these things won't work. You can write them down, but you can't solve them. Yeah.
So on the previous slide, the optimization problem you posed, this is not a convex optimization problem, if I understand correctly. But then when you bring over,
It is, right? It is a convex optimization problem.
So in this case, you can assume that there's going to be one unique.
You can No, so you can claim that local optima is the global optima, but you can't claim uniqueness, because if I ask you to optimize a function like this, then and this is flat,
Yeah.
then this is convex.
Right.
And if I'm at the local optima, I'm at the global optima, but there are multiple of these. Yeah. Okay. Right. So yeah, you can take a look at these resources if you want to know more about STPs. But since it's an STP, we can have the following operational mechanism. So we fix a system Hamiltonian, and we also fix the part of the system that couples to the bath. Then we choose a set of parameters. So we can choose magnetic field, temperature, whatever, to be whatever values we want. And then we can ask MATLAB or whatever to solve this optimization problem for us. If we get it to be less than delta, tau opt, then desired QME is possible, otherwise it's impossible. And the critical claim here is that if you get tau opt greater than equal to delta, and you set delta to be, say, 10 raised to minus 6 or something, delta essentially is a placeholder for 0, then no bath can thermalize the system. We have essentially searched over all baths, all types of couplings, all types of spectral bath functions. You just can't numerically put a value to gamma for which you are getting the thermal state as a steady state. So you're basically dead. You can't, there's no hope. Optionally, these SDP solvers typically will also give you the values of gamma and HLS that they computed for tau opt. So you can solve it, find that delta is basically 10 raised to minus 10, so 0, and it's 0 for this particular value of gamma and HLS. You can take them and then just use them to study dynamics or whatever else you are interested in. So it also is a way to search for such QMEs. I mean, there's obvious caveats here, whether there might be other problems with them. They're not microscopically derived, so we don't know whether they're going to fail on other metrics or not. There's also non-unique, so it's just giving you one of the many possible candidates. So at least for me, I think the important part is just to see when it's not possible rather than when it's possible. Okay, so very briefly, yeah, I'm just gonna briefly talk about we solved the top for an open XYZ spin chain and just some kind of results that we got. So this is our system. So it has some spins that are connected. There's a magnetic field and there's a coupling between them given by G, and there's some anisotropy delta. This is sort of a very well-studied model in transport, like spin transport, energy transport kind of things. So you pick parameters to decide what your magnetic field and coupling strengths are. You pick your temperature, you choose the number of spins coupled to the bath, and then you see what your tau opt is. And here I've connected one spin to the bath. I'm varying the number of spins that are in the system but not connected to the bath. And I'm looking at tau opt versus stuff like coupling strength or temperature. And it's not 0. I mean, 0.01 is definitely not something we would want to call 0. So our conclusion is that, yeah, you can't get a QME that does.
Get a Lindblad form.
Correct, sorry. So you can't get a Markovian QME in Lindblad form that has all the 3 properties we want. So essentially, you can't get all 3 properties for such systems together. Sorry?
You can do this based on an example, you can put it based on.
So even if I get, so here's the claim, right? Even if I get a single example of a system, but set up where I show that numerically for particular parameters, tau opt can't be set to 0, that means that you definitely cannot have a QME that just does it analytically. Because if it did it analytically, I mean, it would do it for all parameter ranges, and you clearly see that you're not. So yeah. I mean, so if you connect G to 0, then it's it's like the thermal state is trivially in some sense a steady state because you don't have coupling between the spins. So I can just put the spins not connected to the bath in their own thermal state and the spin connected to the bath in that thermal state, and it's fine. So setting it to 0 is like you just the system is not connected. So it's sort of a non-question, I would say. Okay. All right. So basically, one spin doesn't work. You just can't do it. This was surprising for us because I expected that you would get tau op to be small, but probably there is no way to analytically derive a QME that does it for every parameter range. But somehow we got it to be positive. Yeah.
So just to understand the result, you're saying that if I have this spin chain.
Yeah.
And I attach my bath to one.
Yeah.
There's no possible bath that I can construct, no interaction I can bring up.
Yeah.
That will thermalize the spin chain.
That will simultaneously thermalize, satisfy local conservation laws, and be in Lindblad form.
And with local dissipation, that's the key aspect.
Yeah, and the local dissipation is something we showed because if you want to get local conservation laws, then you need local dissipation. And if
So you can have a bit other quantum conservation work, but then you have some deficiency.
Yeah.
So they will thermalize, but they are not doing other stuff.
So I could come with the bath, it thermalizes the chain, but doesn't have local conservation, which would mean that spins can jump from place to place.
I guess currents can not match. So in the steady state, you'll compute current from 2 to 3. It won't be the same as 3 to 4.
Okay.
Yeah, that's one. Yeah. So you can so basically the claim is you can't have all three at the same time. You have to pick which ones you want. No, so Lindblad form is the one that you want because it preserves properties of the density matrix. And local is what you want because of local conservation laws. And thermalization is what you want because yeah. I was going to say physics, but I thought that was too general. Anyway, so interestingly, we find that if you couple two spins to a bath, then tau opt is pretty small. So, I mean, if you look at the scaling, last plot was 10 raised to minus 2, and now it's pretty close to 10 raised to minus 10 or 8. So we are already pretty close to the numerical accuracy that CVX gives us. So all of these points are just numerical things. You should not trust them below 10 raised to minus 10 for sure, but basically you can get it to be pretty small. So for 2 qubits to a bath, there is hope, I guess. And the horizontal line is just 10 raised to minus 6. So we just pick that as our tolerance level. You could vary it depending on how much you care about thermalization.
Intuition, right? 2 qubits, and so it's a thermalization of the whole chain
Yes.
by just locally coupling 2 qubits.
Yes. No, in the sense that we all did a poll before doing this, and we thought there's no way 2 qubits is going to work. It's unlikely. You have the whole chain. How can 2 qubits work? Then we found that it works. So then we started rationalizing why it works. But yeah, unless you had given me this plot, I would have argued 50% either way before. Okay, so another, I guess, a weird, interesting thing is that we have to solve this SDP for every parameter regime, right? So you change any parameter in your system, you change temperature, you change magnetic field, you have to redo your SDP to figure out what your QME is. So we find that you can actually change parameters in the bulk. So you can actually change parameters in the part of the system that doesn't couple to the bath. And the same gamma and HLS works because tau is kind of not changing, even though I'm messing around with a bunch of parameters in the bulk. So this is kind of interesting because it makes it operationally easy. I just fix the system and the parameters that determine my coupling. And then I can change parameters in the bulk, and I can use the same QME I've obtained from CVX. And we don't really understand why this happens. We don't even understand very well when it happens. Does it always happen? We don't know. But yeah, something to think about. So yeah, so I want to summarize in brief. So we've gone around systematically searching for physically consistent Markovian QMEs. and we have defined what we mean by physically consistent, Lindblad form, local conservation laws, and thermalization. Our first result is if you want complete positivity and local conservation laws, your QME must act locally. It can only act on the system, part of the system connected to the bath. That also combined with some other known facts about Redfield gives us the fact that Redfield will violate complete positivity unless it happens to be local. So it's kind of nice, fits in well with our current knowledge about Redfield. And adding thermalization led us to introduce the top problem, optimization problem. Its solution shows whether the desired QM is possible or not. If possible, it outputs one choice of a QME because you get the gamma and the HLS numerically from your SDP, so you can use that. So that's a particular choice that does the job for that system at that parameter. So then this is an interesting claim. So if top shows QME is impossible, that means that actually physically the approach to the thermal state must have some non-Markovian character, because we have shown that, okay, physically speaking, we definitely require completely positive and trace constraints, like trace to be conserved. And we definitely require local conservation laws to be conserved because we can show these from the exact problem without any approximations. So if you can't write down a Markovian QME that is satisfying all three, then you must have some non-Markovian character in the exact solution to the problem. So yeah, so in some sense you can also view tau as a measure of how non-Markovian you need to be. But yeah, that's vague. And yeah, the thing I want to really stress is that because we show that you can't get numerical assignment of values to gamma and HLS for particular setups for particular parameters, you definitely can't derive a Markovian QME that simultaneously satisfies all our properties for generic setups. And this is because we show for particular setups it just doesn't work. And this is, I mean, important because people have been trying to get and derive good quantum master equations in Lindblad form that are as accurate as Redfield and do all sorts of things very well. And this is a no-go theorem. You can't get all three for all setups. Okay, so just some things we've been wondering about. So right now we have not really used the top to get a quantum master equation and then use it to study evolution. We don't know if you use it to study evolution, does something really obvious break down or is it mostly fine? So we don't know that, and we'd like to just check it out, see what's happening there. Another thing that I'm very excited about is the top formulation is very versatile. So you're minimizing, in some sense, you're minimizing some metric of something over all possible Lindblad equations, and you can accommodate a wide variety of constraints. So you can optimize a large variety of functions. You can optimize over a large variety of constraints on your gamma. So there might be other situations where bringing in this SDP idea to search for Lindblads that have maybe properties that you are interested in, this SDP formulation might work for that as well. Another thing is that we only looked at, so we didn't really talk about coherences. So coherences of diagonal elements of the steady state density matrix, let's say in energy eigenbasis, and we know that the Redfield equation gives them accurately to leading order. So can we search also, can we add in the requirement that, okay, I know Redfield gives me correct coherences, I want my Lindblad QME to also give me correct coherences. Can we bring that requirement in, write down an SDB for that, and extend top to also give you correct coherences? Yeah, that's something that would be nice. And obviously, in general, this just like all of what I've done is a good way to check whether the required QMEs exist or not. And it's definitely a good way to check when they don't exist for sure. But if you do get that, okay, it might exist numerically, there is tau opt that is small. How do you derive them? How can we find them? What are in what situations do they exist? Yeah, we don't have super good answers to those questions. Yeah, so I'll just end by saying that all code that we used is available on GitHub. So if you want to play around with the SDP, or whatever, you can, at least if you're interested in spin chains, you don't really have to change any code. You can just play around and see. So yeah, that's it. Thank you.